In 1939, in the Annals of Mathematics, Albert Einstein published a paper whose sole purpose was to prove that black holes cannot exist. He was wrong. The object he was trying to argue out of reality had already been found 23 years earlier by a dying artillery officer who mailed the answer to Einstein from a trench on the Russian front and was dead within months. His name now sits on the edge of every black hole in the universe, and almost nobody can tell you who he was. The first exact solution to our theory of space and time described a place where the laws of physics stop working, and for 50 years the finest minds in science, Einstein loudest among them, refused to call it real. It took gravitational waves in 2015 and a photograph in 2019 to confirm that a man dying in 1916 had been right all along. He never knew. Nobody thanked him. And you were never told this, because the story does not end the way science prefers its stories to end. Get comfortable, and if you have not already, subscribe or join, because this is where the buried threads get pulled all the way to the bottom. There is a Patreon as well for the deeper wandering across physics, history, and collapse. Stay to the end, because his surname, in his own language, quietly means Black Shield, and he carried it long before anyone knew the black hole he found would need one. Let's go back to where this began. In the winter of 1915, on the Eastern Front of the First World War, a German artillery officer in his 40s was slowly dying of a disease that was blistering his skin from the inside out. And in the few weeks of clarity he had left, he did something that Albert Einstein, at the very height of his powers, had just implied to the world was probably out of reach. He solved Einstein's equations, not approximately, not with the clever shortcuts and educated guesses that Einstein himself had been forced to lean on. He solved them exactly, in closed form, on paper, in between calculating the arcs of artillery shells meant to fall on Russian trenches. And what dropped out of that exact solution was the first honest mathematical description of an object that would not be accepted as real for another 50 years. A place where space and time change roles. A place where the laws of physics stop describing anything at all. A hole in the bottom of reality. His name was Karl Schwarzschild. The letter he mailed to Einstein from the front, the letter that carried the answer folded inside it, has outlived him now by more than 100 years. He himself was dead within months of sealing the envelope. Here is the part that never makes it onto the poster. The object he found, the thing we now casually call a black hole, lives in the public imagination as one of two stories. In the first story, it is a triumph of modern hardware, something humanity finally pinned down in our own lifetime, with gravitational wave detectors and that famous orange photograph from 2019. In the second story, it is Einstein's crowning prophecy, the natural child of general relativity, the monster the great man saw coming and warned us about. Both stories are false. The black hole was not first found by a machine in the 21st century. It was found by a sick man with a pencil in a war zone in 1916. And Einstein did not predict it, did not want it, and spent a serious fraction of the rest of his life trying to prove it could not be there. In 1939, he put his name on a paper arguing that the very object Schwarzschild's mathematics pointed to was a physical impossibility. He was wrong. The mathematics was right. And the man who had done that mathematics was already 23 years in his grave. That is the story I want to walk you through tonight, because the more time you spend inside it, the less it looks like a triumph and the more it looks like something reality tried to keep sealed. There is a single question sitting underneath all of it, and I want you to hold on to this question, because we are not going to answer it, and neither has anyone else. The question is not whether black holes exist. We settled that. The question is, what is actually at the centre of the thing Schwarzschild wrote down, at the very bottom of his solution, and why the most successful theory in the history of physics predicts that place, and then, at the exact same point, predicts its own total collapse. The theory draws you a map straight to the abyss, and then the map dissolves in your hands. Schwarzschild found the spot where the ink runs out, and I do not think it is an accident that he found it while his own body was doing something disturbingly similar. To feel why any of this matters, you have to understand what the word exact means to a physicist, because it is doing almost all of the work in this story. And it is the reason a relatively obscure astronomer on a battlefield managed to leapfrog Einstein on Einstein's own theory in a matter of weeks. In November of 1915, after nearly a decade of grinding, false starts, and one genuinely embarrassing public retraction, Einstein finally arrived at the field equations of general relativity. He presented them to the Prussian Academy of Sciences in Berlin across a series of lectures that month, with the final form landing on the 25th of November. These equations are a statement about gravity, but they are nothing like the tidy gravity you learned as a kid. Newton gave you a clean formula. Two masses, a distance between them, a force. You can solve it on a napkin. Einstein's equations say something far stranger. They say that matter and energy tell space-time how to curve, and the curved space-time tells matter how to move, and both sides of that sentence depend on each other at the same instant. Mathematically, this makes them what is called non-linear, and non-linear is a polite word physicists use for a nightmare. The curvature depends on the matter, but the matter's motion depends on the curvature, which depends on the matter. Everything is tangled into everything else. There are 10 of these equations, all knotted together, and Einstein himself, when he wanted to test his brand new theory against the orbit of Mercury, did not solve them. He could not. He approximated. He used a method that gets you close to the answer without ever landing on it, the mathematical equivalent of describing a coastline by walking most of the way around it in the fog. It worked well enough to explain the wobble in Mercury's orbit that had haunted astronomers for half a century, and that alone was enough to make Einstein famous. But an approximation is a confession. It says, I cannot tell you exactly what my own theory does here. I can only tell you roughly. Now put yourself on the Eastern Front. It is December. Schwarzschild is 42 years old, which already makes him an oddity in a war fought mostly by boys. He is not a soldier by trade. He is one of the most respected astronomers in Germany, the director of the Astrophysical Observatory in Potsdam. A man whose work touches optics, stellar atmospheres, photographic photometry, the mechanics of orbits, whole territories of science. He did not have to be there. He volunteered in 1914 at an age and a level of prestige where absolutely no one would have questioned him staying home. And he ended up assigned to an artillery unit computing the trajectories of shells. Which is its own kind of bitter irony, because the same equations that let you drop a shell precisely onto a distant enemy are the polite Newtonian solvable cousins of the monstrous non-linear equations he was about to crack in his spare time. He gets his hands on Einstein's November paper, and within days, in the middle of a war, a man doing ballistics by day sits down and finds the exact solution to Einstein's field equations for the simplest interesting case, the gravitational field around a single spherical mass, a star, a planet, any round object sitting alone in space. Einstein had the equations for barely a month and had only managed to approximate. Schwarzschild solved them clean. On the 22nd of December 1915, he writes to Einstein to tell him. And the letter is the reason I fell into this story in the first place, because it is one of the strangest documents in the history of science. Here is a man surrounded by artillery fire, sick, and what he writes is almost serene. He tells Einstein that the war has been kind enough to him, that despite the heavy gunfire at a decidedly earthly distance, it had allowed him to take this walk, as he put it, in the land of Einstein's ideas. Read that again and sit with it. A dying man on a battlefield describing the interior of the newest and most difficult theory of gravity as a landscape he got to stroll through while the shells came down around him. He was not being poetic for effect. That is genuinely how his mind worked. He had found a door in Einstein's equations, and he had walked through it, and on the other side he found something he did not fully understand, and he was calm about it in the way that only a person who is already at peace with dying tends to be. Einstein wrote back on the 9th of January, 1916, and his reaction tells you exactly how unexpected this was. He said he had not expected that the exact solution to the problem could be formulated so simply. Read that closely too. Einstein, the author of the theory, was surprised that his own equations could be solved at all in this case. And more surprised that the answer was clean. He thought nature would be messier here. It was not. Schwarzschild had reached into the tangle and pulled out something almost elegant. Einstein was impressed enough that he personally presented Schwarzschild's paper to the Prussian Academy on the 13th of January, 1916, on the author's behalf, because the author was in a trench in Russia and could not exactly attend. But here is where the calm surface of this story develops its first crack, and it is the crack that everything else falls into. Because when you actually look at the solution Schwarzschild handed over, the thing is not entirely well behaved. It describes the geometry of space and time around a mass beautifully, cleanly, for almost every distance you could care about. And then, at one specific distance from the centre, the equations do something ugly. A term in the solution blows up, divides by 0, goes to infinity. And at a second location, right at the dead centre, at 0 distance from the middle, it does it again, worse. The map Schwarzschild drew has 2 places on it where the ink smears into an infinite black stain. 2 singularities, and the entire drama of the next 50 years, the reason Einstein turned against his own theory's implications, the reason careers were made and reputations were risked, all of it comes down to a fight over what those 2 smears on the map actually mean. Are they real places you could fall into? Or are they just flaws in the paper, artifacts of how Schwarzschild happened to draw the thing? Schwarzschild himself did not get to have that fight. He was out of time. And I want to be honest with you about the timeline, because the story gets told carelessly and the truth is heavier than the careless version. The popular telling says he solved the equations and died weeks later, as though the abyss reached up out of the mathematics and pulled him down for looking. That is too clean. The real sequence is slower, and if anything sadder, he wrote the letter in December. Einstein read the first paper to the Academy in January. Schwarzschild then wrote a second paper on the interior of such a mass, which reached Berlin in February. And then his health, which had been failing on the Russian front, collapsed entirely. He was invalided home to Germany. And on the 11th of May 1916, in Potsdam, he died. He was 42. It was not weeks between the abyss and the grave, it was months. But look at what those months contained. In roughly the last half year of his life, gravely ill, this man produced the first exact solution to general relativity, a second paper extending it, and separate work on the quantum theory of the atom that was also ahead of its time, all while his body was failing in a way the medicine of 1916 could do absolutely nothing about. The abyss did not kill him. But he did walk up to the edge of it, look in, write down what he saw, and then die before a single other human being on Earth understood what he had actually been looking at. That is the shape of the thing. He found the bottom of the theory, and then he was gone. and the answer he mailed out sat in a journal for 2 generations while the rest of physics argued about whether he had found a real place or just made a mistake. To understand why that argument lasted 50 years, and why it eventually broke in Schwarzschild's favour in the most unsettling way possible, you have to understand the 2 smears on his map one at a time. Therefore we start with the outer one, the distance where the equations first blow up, because that distance turned out to have a name, and a size you can calculate for any object in the universe, including the chair you are sitting in and the planet under it. And once you can calculate it, you cannot stop seeing it. Every object you have ever seen has a second size, not the size you can measure with a ruler, a hidden size, a threshold, and if you could ever squeeze the object down past that threshold, the universe would close over it like water over a dropped stone, and it would vanish from the outside world forever. Your body has one. The planet under your feet has one. The sun has one. This is the thing Schwarzschild found at the outer edge of his solution, the first place where the equations blow up, and it is the reason his name is now attached to the most final boundary in physics. We call it the Schwarzschild radius. And once you understand how to calculate it, the sky stops looking like a decoration and starts looking like a collection of objects that have each been given a specific distance at which they would be permitted to disappear. The formula itself is almost insultingly simple for something this consequential. You take the mass of the object, multiply it by 2 and by Newton's gravitational constant, and divide the whole thing by the speed of light squared. That is it. 3 quantities: a mass, a universal constant, and the speed of light. What comes out the other side is a distance, and that distance marks a sphere. If you could compress the entire mass of the object down to fit inside that sphere, then at the surface of the sphere, the pull of gravity becomes so severe that the speed you would need to escape it reaches the speed of light. And since nothing can go faster than light, nothing escapes. Not a rocket, not a signal, not a single photon. The sphere becomes a one-way door. Things fall in. Nothing comes back out. Not ever. Let me make the numbers physical, because this is where it stops being abstract. Take the sun. The sun is about 1,400,000 kilometers across. It is a genuinely enormous object, so large that around 1 million Earths would fit inside it. Now calculate its Schwarzschild radius. The answer is about 3 kilometers. 3. To turn the sun into an object that swallows light, you would have to take that entire colossal ball of burning plasma, all of it, and crush it down until it fit inside a sphere roughly the size of a small town. Not a smaller star, not a dim ember, a sphere you could walk across in under an hour, containing the full mass of the sun, wrapped in a surface that nothing can climb back out of. Now do it for the Earth. The whole planet. Every ocean, every mountain, the molten core, all of it. The Schwarzschild radius of the Earth is about 9 millimeters. You could hold it in the palm of your hand. If some impossible vice compressed the Earth down to the size of a marble, a grape, something you could lose in the carpet, it would become a black hole. And the surface of no return around it would be about the width of a small coin. Everything you have ever known, the entire stage of all of human history, has a hidden threshold smaller than a walnut, and on the far side of that threshold, the planet would simply be gone from the universe, leaving behind only its gravity and a dark sphere where the world used to be. I want to correct something here, because this is roughly the point where the popular version of the story goes wrong, and the real version is stranger. When people first hear this, they picture the Schwarzschild radius as a kind of surface, a membrane, a physical shell you would smack into. It is not. If you fell toward a large enough black hole, you would cross the Schwarzschild radius. The point of no return, without feeling anything happen at all. No barrier, No flash, no membrane tearing, nothing local marks the boundary. You could pass the most absolute threshold in all of physics and not even know you had done it. The horizon is not a place in the way a wall is a place. It is a property of the whole geometry. A statement about which events can ever again send a signal to the outside universe and which cannot. From your point of view falling, nothing changes at the crossing. From the universe's point of view, you are already gone. Both of those are true at the same time, and holding them both in your head at once is the first genuinely disorienting thing this solution does to you. And here is the correction that matters even more, because it is the one the whole culture gets backwards. This idea, the dark object that traps its own light, did not begin with Einstein, and it did not begin with modern astronomy. In 1783, more than a century before any of this, an English clergyman and natural philosopher named John Michell wrote a letter to the Royal Society describing what he called a dark star. He reasoned, using nothing but Newton's gravity and the assumption that light had some kind of speed, that if you made a star massive enough, its escape velocity would exceed the speed of light, and the light would fall back down, and the star would be invisible. A Frenchman, Pierre-Simon Laplace, published a similar idea in 1796. The ghost of the black hole was already haunting physics before the French Revolution. But their dark stars were a Newtonian curiosity, a clever bit of arithmetic about fast-moving light particles being tugged back by gravity, and nobody could take them very far. What Schwarzschild found was not that. What Schwarzschild found was that the very fabric of space and time, according to Einstein's equations, tears itself into a configuration around a sufficiently compressed mass, where the inside and the outside are causally severed. It is a far deeper and far more disturbing statement. The Newtonian dark star merely traps light like a ball thrown too slowly. The Schwarzschild solution says the geometry of reality itself folds closed. To see just how far it folds, you have to look at what the mathematics says happens to space and time once you cross the outer threshold, and this is the part that genuinely unsettled me the first time I understood it properly. In ordinary life, you have a choice about where you go in space, and no choice at all about where you go in time. You can walk north or south, left or right, up or down within limits, but you cannot choose to stop moving toward the future. Tomorrow is coming whether you like it or not. Time only runs one direction for you, and you are dragged along it. Inside the Schwarzschild radius, according to the solution, the roles of space and time change places. The direction that points toward the center of the black hole, toward that second singularity at the very middle, stops behaving like a direction in space and starts behaving like the direction of time. Which means that falling toward the center becomes exactly as unavoidable as falling toward tomorrow. Once you are inside, you cannot steer away from the center any more than you can steer away from next Tuesday. Every road leads down. The center is not a place you might hit. It is a moment in your future that you cannot avoid arriving at. The same way you cannot avoid arriving at the next second of your life. The geometry has rewritten your options. It has taken the one axis you never had control over, time, and pointed it straight down the throat of the thing. Sit with that, because it is not science fiction, and it is not a metaphor I am reaching for to make this sound scarier than it is. That is what the equations say. That is what falls out of the same solution Schwarzschild mailed to Einstein from the Eastern Front. Cross the boundary and the center of the black hole stops being somewhere you could go and becomes something that is going to happen to you, a fixed appointment in your own timeline, and the universe will not permit you to reschedule. Let me take you on that fall, because the experience of it, worked out from the same equations, is stranger than any horror anyone has ever invented, and it turns the abstraction into something you can feel in your stomach in a way the bare numbers never will. Suppose you are falling in, feet first, toward one of the large black holes, the supermassive kind, millions of times the mass of the sun. Because those are the gentlest, and they will let you last the longest. Long before you reach the horizon, you are already moving at a serious fraction of the speed of light, pulled faster and faster. You look down toward the black circle that is swelling to fill your vision, and then you look back up at the universe you are leaving, and something has happened to the sky. The entire universe above you has been squeezed into a shrinking, brightening disk, all of its light piled up and shifted toward the blue by your speed and by the gravity. The whole of creation compressed into a single jewel of fire directly overhead, while everything around the edges of your view goes utterly black. You are falling into darkness with the entire cosmos collapsing into one brilliant point behind you. And then you cross the horizon, and you feel nothing. There is no barrier, no jolt, no membrane, exactly as I said. For a large enough black hole, the tidal forces at the horizon are gentle, and you sail straight across the most absolute boundary in all of physics. The point past which the outside universe will never see you again, and you can never send it another signal, with no local sign that anything has changed at all. You might not even know the instant it happened. Behind you, the outside universe has just slipped out of your reach forever. Ahead of you is the center. And the center is no longer a direction you can decline. Every path you could take, every way you could steer, every last thing your rockets could do, all of them now lead down, because the geometry has rotated the center into your future, and you are falling toward it the way you fall toward the next minute of your life, with no possibility of refusal. Now, the clock is running. For a supermassive black hole, you might have a few seconds of your own time between crossing the horizon and reaching the center, and in those final seconds, the thing that has been gentle turns savage. As you fall toward the point at the middle, the difference in gravity between your feet, which are nearer, and your head, which is farther, begins to grow. At first it is a faint stretching, a tension along the length of you. Then it is a pull. Then the pull between your head and your feet climbs past anything flesh and bone can survive, and you are drawn out, longer and thinner, stretched along the line of your fall, while at the same time you are crushed inward from the sides, because the space around you is narrowing toward a point. Physicists named this spaghettification, and the joke hides what it really is, which is the tidal force rising toward infinity as the curvature of space-time rises toward infinity, faster and faster in your last moments, until the stretching and the crushing and the curvature itself all pass beyond any finite value at exactly the same instant. And that instant is the singularity. Not a wall you strike, not a floor you land on. A moment in your future arriving at which the forces acting on what used to be your body become infinite, and the theory that has described every step of your fall with flawless precision produces, for the first and only time, no answer at all. It does not tell you what becomes of you there. It cannot. It has reached the edge of what it is able to say, and so, at that same instant, have you. And here is the loneliness written into the mathematics. While you live that fall as a matter of seconds, anyone watching you from a safe distance never sees you cross the horizon at all. They see you slow and redden and dim and hang at the very edge, fading toward invisibility, frozen in the last moment of your approach, and they go on seeing that faint frozen ghost of you for the entire remaining history of the universe. You experience your death in seconds. The outside universe experiences your death as something that never quite finishes, a smear of dimming light pinned to a dark surface for eternity. Both are true. The theory insists on both at once, and there is no higher fact that reconciles them, no shared answer to the simple question of when or whether you are gone. All of which assumes that anything ever truly falls in, that real matter in the real universe genuinely makes this journey down to the genuinely infinite center. And that assumption is exactly where the whole subject fractured for half a century. You can accept every step of the fall as valid mathematics and still insist that nature keeps some trick in reserve, some flaw, some hidden mechanism that halts matter before it ever reaches the bottom. That is the crack the next 50 years poured into. Now, the correction that the whole popular story hinges on. People say Einstein predicted black holes. He did not. People say Einstein discovered them. He did not. And people say Schwarzschild discovered black holes, and that is closer but still wrong, and the difference is the whole story. What Schwarzschild discovered was the solution, the exact geometry, the mathematics of the field around a compressed spherical mass. Whether that mathematics described a real object that could actually form in the universe, an object matter could genuinely collapse into, was a completely separate question, and it is a question Schwarzschild never got to ask, because he was dead within months, and it is a question the rest of physics would spend the next 50 years actively refusing to answer. The solution existed from 1916. The willingness to believe the solution described something real did not arrive until the 1960s. That gap, that 50-year silence, is not a story about slow instruments or missing data. It is a story about the most brilliant physicists of the 20th century looking directly at a consequence of their own best theory and deciding, over and over, that it simply could not be allowed to be true. And the man leading that refusal, the single most important voice arguing that Schwarzschild's abyss could not physically exist, was Einstein himself. But before we get to Einstein turning against his own creation, you need to understand what he was so afraid of, because he was not being stupid and he was not being stubborn for no reason. He was staring at the second singularity, the one at the center, the one at the very bottom of the solution, at zero distance from the middle, where the outer threshold we have been discussing is merely a locked door, and the thing behind the door is far worse. Because everything I have told you so far, the horizon, the point of no return, the swapping of space and time, all of that is the polite part of Schwarzschild's solution. All of that is survivable to write down. The horizon, it would turn out, is not even a real singularity at all. It is a kind of illusion, an artifact of the way Schwarzschild happened to draw his map. And once physicists learned to redraw the map, the horizon smoothed out into something almost ordinary. But the thing at the center does not smooth out. You can redraw the map any way you like. You can use every coordinate system ever invented. And the center stays broken. It stays infinite. It stays a place where the theory that predicts it screams and dies. Therefore, we have to go to the center. We have to look at the thing Einstein could not accept. And we have to talk about the difference between a flaw in the map and a hole in the territory, because that single distinction is what took physics half a century to understand, and it is the distinction that turns this from a story about a clever solution into a story about the edge of reality itself. Here is a distinction that sounds like pedantry and is actually the difference between a smudge on a photograph and a wound in the thing photographed. When a set of equations produces infinity, there are two completely different reasons it might do that, and telling them apart took some of the best minds of the century the better part of 50 years. The first reason is that something has genuinely gone wrong with reality at that spot. The infinity is real. The territory itself is broken. The second reason is far more embarrassing. The infinity is not in the territory at all. It is in your map. You chose a bad way to draw the thing, and your drawing blew up at a spot where the actual landscape is perfectly fine. The equations lied to you, not because reality is broken there, but because your coordinates are. Think about the North Pole on a globe. Every line of longitude, every meridian, all of them converge to a single point at the top of the world. If you built a mathematics of location purely out of longitude, that point would look like a catastrophe. Longitude becomes meaningless there. All values collapse into one spot. Your equations would throw up an infinity and tell you the North Pole is a place where geography itself breaks down. But of course, it is not. You can stand at the North Pole. It is cold and it is ordinary, and the ground is perfectly solid. There is nothing singular about the place. The singularity was never in the Earth. It was in your decision to describe the Earth using longitude, a coordinate system that happens to fall apart at the poles. Change your map, use a better set of coordinates, and the fake catastrophe simply vanishes. The pole was fine all along. For decades, nearly everyone who looked at Schwarzschild's solution assumed both of its blow-ups were real. They lumped them together and spoke of the Schwarzschild singularity, singular, as though the horizon at the outer radius and the point at the centre were the same kind of horror. They treated the event horizon as a genuine edge of reality, a place where matter would be torn apart by infinite forces, a wall of broken physics surrounding the object. And this mistake, this conflation of the map with the territory, is a large part of why the whole idea was dismissed for 2 generations. If the horizon itself is a place where physics detonates, then obviously no real object could have one. Obviously it was a mathematical fiction. Obviously nature would never actually build such a thing. The reasoning was sound. The premise was wrong. The person who first saw clearly that the premise was wrong was not a household name, and his life rhymes with Schwarzschild's in a way I find hard to ignore. Georges Lemaître was a Belgian priest and physicist, born in 1894, and like Schwarzschild he had gone to the First World War, serving as an artillery officer, doing the same grim arithmetic of trajectories that Schwarzschild had done. He is better known today as the man who first proposed that the universe is expanding, and that it began from what he called a primeval atom, the idea that would later be renamed the Big Bang, mostly by people trying to mock it. In 1932, Lemaître worked through the Schwarzschild solution carefully and reached a conclusion that almost nobody was ready to hear. The singularity at the Schwarzschild radius, he showed, was not real. It was a fiction produced by the coordinates. A better choice of coordinates made it disappear entirely, exactly like the North Pole under a better map. The horizon was a genuine boundary, a point of no return, but it was not a place where physics broke. Nothing infinite happened there. You could fall right through it, as I said earlier, feeling nothing, because there was nothing there to feel. This should have been a turning point. It was mostly ignored. And the reason it was ignored brings us to the abdication at the heart of this story. Because the people whose job it was to take this seriously did not merely fail to notice it. They actively did not want it to be true. And when confronted with it, they reached for reasons to look away. But before we get to the men who looked away, we have to finish the autopsy of the solution, because Lemaître only cleared away the outer infinity, the fake one. He removed the smudge from the map, and when the smudge was gone, when the horizon was revealed to be nothing but a threshold you could cross without harm, the second infinity was still there, at the centre, and it did not go away under any map anyone could draw. This is the crucial point, and it is the one I want you to hold above all the others. The horizon is a coordinate illusion. The centre is not. You can change coordinates until you run out of ideas, and the point at 0 distance from the middle stays broken in every single one of them. There is a way to prove this that does not depend on any choice of map, a quantity you can calculate that measures the actual curvature of spacetime itself, the real bending of the real geometry, independent of how you have chosen to describe it. At the horizon, that quantity is finite, perfectly reasonable, a large but ordinary number. At the centre, that quantity runs to infinity, not because of longitude, not because of a bad map. because the curvature of space-time genuinely, invariantly, coordinate independently, becomes infinite there. The territory is broken. There is a real hole. And now you have to ask what an infinite curvature of space-time actually means, physically, for anything unlucky enough to arrive there, and the answer is that it means the end of description. Curvature is what you feel as tidal force, the difference in gravity between your head and your feet. Near any strong source of gravity that difference stretches you, a process physicists have named, with rare dark humour, spaghettification, as you approach the centre of a black hole, that stretching does not level off. It climbs without limit. The force trying to pull your head away from your feet becomes arbitrarily large, then larger than any number you can write, then infinite. Density does the same. All the mass that fell in, an entire collapsed star, more mass than the sun, is compressed toward a single point of zero size, which means the density, mass divided by volume, divides a finite number by zero and returns infinity. Every quantity the theory tracks, curvature, density, tidal force, the very steepness of time itself, goes to infinity at the same point. And a physical theory that predicts infinity is not making a prediction. It is confessing. It is telling you, in the only language it has, that it has reached the edge of what it can describe and has nothing left to say. That is the thing Schwarzschild found at the bottom of his solution. Not a very dense object, not a very deep well, a place where general relativity, the most precise and successful theory of gravity ever written, the theory that has passed every experimental test for over 100 years, stops working. And it does not stop working out at the fringes of the cosmos, or in some exotic scenario that never happens. It stops working at the centre of every black hole in the universe, and there are more black holes than anyone once dreamed, and every one of them has this same broken point at its heart. A point where the theory that predicts the black hole also predicts its own failure to describe the black hole. The equation contains the location of its own death. I said at the very beginning that there was a single question underneath all of this, and that we would not answer it, and now you can see the question with more of its teeth showing. What is actually at the centre of a black hole? And the honest answer, the answer physics gives you today, in the 2020s, with all our instruments and all our theory, is that we do not know. Because the only theory that tells us the centre exists is the same theory that breaks down completely the moment we ask, what is there? General relativity draws you a map with total confidence, leads you all the way to the centre, and then the map simply ends. Not with a coastline, not with an edge marked here be dragons, with an infinity, which is mathematics for a screen. And every attempt to see past that screen, to describe the centre with something better than general relativity, runs into the deepest unsolved problem in all of physics, the problem of uniting gravity with quantum mechanics. A problem that has defeated everyone who has ever attacked it for the better part of a century, Einstein included. I want to plant something here that will matter later, and I want you to file it away the way you would file away a detail in a story that you sense the author left deliberately. The singularity at the centre is not really a place inside the universe. Think about what it is. It is the point where the description of the universe fails. It is where the theory that defines space and time can no longer define space and time. In a real sense, it is not a location in reality, so much as the edge of reality's own ability to be described. A hole not in space, but in the map of everything, sitting at the bottom of an object that the universe manufactures routinely. By the billions every time a large enough star runs out of fuel and falls in on itself. Schwarzschild reached that edge on paper in 1916, and the closer you look at the timing, at what was happening to the man himself as he wrote, the harder it becomes to read the whole thing as a coincidence. He found the point where the description of reality dissolves into infinity at the precise moment his own physical reality was dissolving, cell by cell, under a disease that was erasing the boundary of his own body. I do not know what to do with that parallel. I only know it is there, in the record, in the dates, and that once you see it, you cannot unsee it. But a broken point at the centre of the mathematics is one thing. Whether nature ever actually builds such a thing, whether real matter in the real universe ever truly falls all the way down into that infinite centre, is a different question entirely. And it is the question that split physics down the middle. Because you can accept that Schwarzschild's solution is mathematically valid and still insist that no real star would ever collapse that far. You can admit the map has a hole in it and still deny that anything in the territory ever falls through. And that is exactly the position that the greatest physicist of the 20th century took, in print, with his full authority behind it. Therefore, we have to talk about the 50-year refusal, and we have to start with the name that makes it almost impossible to believe. We have to start with Einstein trying to kill the thing that came out of his own equations. In 1939, Albert Einstein published a paper whose entire purpose was to prove that black holes cannot exist. It appeared in the Annals of Mathematics, one of the most respected journals in the world, and its argument was aimed directly at the Schwarzschild radius. Einstein took a cluster of particles held together by their mutual gravity and asked what would happen if you tried to squeeze that cluster down toward the critical radius where the horizon would form. He showed, correctly within his setup, that the particles would have to orbit faster and faster as the cluster shrank, and that to hold themselves together right at the Schwarzschild radius, they would need to move at the speed of light, which is impossible. From this he drew the conclusion he had clearly wanted to reach all along. He wrote that the Schwarzschild singularity does not appear because matter cannot be concentrated arbitrarily. In plain terms, he was saying nature has a built-in safeguard. Matter simply refuses to compress that far. The horizon is a mathematical mirage that physical matter will never actually produce. The abyss cannot form. It is forbidden. He was wrong. And the reason he was wrong is almost unbearably simple in hindsight. Einstein had studied a stable static cluster, a collection of particles in steady orbits, and asked whether it could sit forever at the edge of forming a horizon. Of course it could not. But that was never the dangerous case. The dangerous case is not a cluster politely holding station. The dangerous case is collapse. A massive star that has burned through its fuel and has nothing left to hold it up, falling inward under its own weight, with no steady orbits and no equilibrium and nothing to stop it. Einstein analysed the one scenario guaranteed to avoid the problem and concluded the problem never happens. It is one of the most consequential wrong answers a genius has ever committed to print, and physics treated it as gospel for a generation, in large part because of whose name was on it. Now here is the detail that should genuinely unsettle you, because it turns this from a story about one man's error into a story about the whole discipline looking away at the same moment. That exact same year, 1939, while Einstein was publishing his proof that gravitational collapse to a singularity could not happen, two physicists in America published the proof that it could. Their names were Julius Robert Oppenheimer, who would later become far more famous for a very different reason, and his student Hartland Snyder. Their paper was called On Continued Gravitational Contraction, and it appeared in the journal Physical Review. In it, they did the calculation Einstein had avoided. They took a massive star, removed its ability to hold itself up, and let general relativity dictate what happened next. And what happened next was collapse, all the way down, past the point of no return, through the horizon, toward the centre. They described how, from the point of view of someone watching from far away, the collapsing star would appear to slow as it approached the Schwarzschild radius, its light stretching and dimming and reddening, until the star seemed to freeze at the horizon and fade from view. But from the point of view of the surface of the star itself, there was no freezing at all. The surface fell straight through the horizon in a finite amount of its own time, and continued down toward the singularity. They had, in 1939, written the first correct modern description of the formation of a black hole, not the mathematics of an idealized eternal object, but the actual physical process by which a dying star becomes one. And almost nobody read it, because the paper was published on the 1st of September, 1939, which is the day Germany invaded Poland and began the Second World War. The single most important paper on gravitational collapse for the next 2 decades came out on the morning the world caught fire, and it sank without a trace. Oppenheimer himself would be pulled into the Manhattan Project and would never return to the problem. The man who first showed that Schwarzschild's abyss was not just mathematically valid, but physically inevitable, walked away from it to build a different kind of abyss, and he did not look back. The timing is so cruel, it reads like something a novelist would be told to cut for being too on the nose. This is what I mean when I say the 50-year silence was not about missing data. In 1939, the answer was already on the table, in print, in a major journal. Correct. The refusal to accept it was not a shortage of evidence. It was a decision, repeated across the field, to treat the collapse as an unphysical curiosity, and the decision had a lot to do with the fact that the loudest and most authoritative voices in physics did not want it to be real. Einstein did not want it. And a few years earlier, in a scene that has become infamous, the most influential astrophysicist in the world had already made an example of a young man who dared to suggest that stars could collapse without limit, and the memory of that public humiliation hung over the whole subject like a warning. The young man was Subramanian Chandrasekhar. In 1930, at the age of 19, on the longboat journey from India to England to begin his studies at Cambridge, he did a calculation that should have changed everything decades before it did. He was thinking about white dwarfs, the dense burnt-out cores that stars like our sun become when they die. The accepted wisdom was that every star, no matter how massive, would eventually settle down as a stable white dwarf, held up forever against gravity by a quantum effect called electron degeneracy pressure, a kind of resistance that electrons put up when you try to pack them too closely together. Chandrasekhar combined that quantum effect with Einstein's special relativity, and he found something the accepted wisdom had missed. The support has a limit. If the mass of the dead core is greater than about 1.4 times the mass of the Sun, the electrons are forced to move so fast that relativity caps their resistance, and the pressure can no longer hold. Above that mass, which we now call the Chandrasekhar limit, nothing known can stop the collapse. The star must keep falling in on itself. A 19-year-old had found, on a boat, the doorway to the black hole, the mass threshold beyond which a dying star has no choice but to fall toward Schwarzschild's center. He developed the work carefully over the next several years, and in January of 1935, he presented it to the Royal Astronomical Society in London. Sitting in the room was Arthur Eddington, the towering figure of British astrophysics, the man who had led the expedition that confirmed general relativity in 1919 and made Einstein a global celebrity, the most authoritative astronomer alive. Chandrasekhar had shown Eddington his results beforehand, and Eddington had said nothing to warn him. And then, immediately after Chandrasekhar finished speaking, Eddington stood up and tore the work to pieces in front of the entire society. He called the idea of unlimited collapse a reductio ad absurdum, a result so obviously ridiculous it disproved the reasoning that led to it. He said, in words that have echoed through the field ever since, that there ought to be a law of nature to prevent a star from behaving in this absurd way. He did not have a mathematical refutation. He had authority and contempt and the certainty that nature simply would not permit anything so grotesque. And it was enough. The room deferred to Eddington. Chandrasekhar, 24 years old and humiliated, found his result effectively frozen out of mainstream acceptance. He eventually left the study of stellar collapse entirely and moved to the United States, and he did not receive the recognition he deserved for that calculation until he was awarded the Nobel Prize in 1983, almost half a century after Eddington stood up and buried it. Count the pattern, because it is the same pattern every time. Schwarzschild found the solution and died before anyone understood it. Lemaitre showed the horizon was not a real singularity and was ignored. Chandrasekhar found the mass limit that forces collapse and was publicly ridiculed by the most commanding figure in his field. Oppenheimer and Snyder showed collapse actually produces a black hole and were drowned out by a world war. 4 correct results across more than 20 years, each one a piece of the same truth, and each one dismissed, buried or forgotten, not because anyone had shown it was wrong, but because the conclusion it pointed to was too strange and too uncomfortable and too offensive to physical intuition for the establishment to swallow. This was not a conspiracy. Nobody met in a room and agreed to suppress the black hole. It was something quieter and in a way more damning. It was an entire discipline, populated by the smartest people on Earth, collectively deciding for 50 years that the clear implication of their own best theory could not possibly be true, and looking away, again and again, from the hole at the centre of the map. And while they looked away, the thing they were refusing to believe in was out there in the real sky, in enormous numbers, doing exactly what the mathematics said it would do. Every massive star that had ever exhausted its fuel and collapsed had already done this. The universe had been building Schwarzschild's abyss continuously for billions of years, entirely indifferent to whether the physicists of Earth were emotionally prepared to accept it. The objects were real the whole time. The only thing that was missing was our permission to see them. That permission finally began to arrive in the late 1950s and early 1960s. And when it broke fast. And it broke because a new generation showed up who had not been in the room when Eddington sneered and did not particularly care what Einstein had wanted to be true. But the way it broke, the specific discoveries that forced the abyss back into physics, did not make the thing less disturbing. They made it worse. Because the more clearly physicists understood the black hole, the more they realized that the singularity at the center was not a fragile feature that only appeared in Schwarzschild's perfectly round, idealized case. It was not something you could dodge by making the collapse a little messy, a little lopsided, a little more realistic. Therefore, we have to look at what happened when a mathematician set out to prove the singularity was avoidable. An artifact of too much symmetry, and instead proved the exact opposite. We have to look at the moment physics discovered that once collapse begins, the abyss at the center is not a possibility. It is a certainty. And there is no version of the story where matter falls in and something reasonable happens instead. For a long time there was a comforting escape hatch available to anyone who did not want to believe in the singularity, and it was a reasonable one. Schwarzschild's solution assumed perfect spherical symmetry, a flawless, idealized ball of matter collapsing in on itself with perfect evenness, every part falling toward the exact center in perfect balance. And real stars are not like that. Real stars spin, they bulge, they are lumpy and turbulent and asymmetric. Perhaps, the hope went, the singularity was an artifact of that unrealistic perfect symmetry. Perhaps in a real messy off-center collapse, all that infalling matter would not converge on a single point. It would swirl and miss and slew past itself. The way water going down a drain does not all meet at one mathematical spot. Perhaps the infinities only appeared because Schwarzschild had assumed an impossible tidiness, and nature's imperfection would save us from the abyss. It was the last respectable place to stand if you wanted the singularity to be a mirage. In 1965, a 34-year-old British mathematician named Roger Penrose took that escape hatch and sealed it shut forever. His paper was titled Gravitational Collapse and Space-Time Singularities, and it ran to barely 3 pages in the journal Physical Review Letters, and it is one of the most important 3 pages in the history of the subject. Penrose did not assume spherical symmetry. He did not assume anything about the shape of the collapse at all. Instead, he imported a completely new kind of mathematics into the problem, the mathematics of topology, which studies the global shape and connectivity of spaces rather than their precise measurements. He introduced an idea he called a trapped surface, a region so warped by gravity that every direction light can travel, even straight outward, is bent back inward. Once a trapped surface forms, light itself has nowhere to go but further in. And Penrose proved, with the collapse shape left completely arbitrary, lumpy or smooth or spinning or still, that the formation of a trapped surface guarantees the formation of a singularity. Not maybe, not in the idealized case. Always, given only that gravity is attractive and a couple of other mild and reasonable conditions. Once collapse passes a certain point, a singularity at the end of it is mathematically unavoidable. This is the moment the escape hatch closed. The singularity was not a fragile consequence of too much symmetry. It was robust. It was generic. It was what general relativity predicts for the end of any sufficiently advanced collapse, no matter how messy, no matter how real. The imperfection of real stars does not save you. It changes nothing. Every hope that nature would find some graceful way to avoid the infinity was extinguished in 3 pages. And this is the work for which Penrose was finally awarded the Nobel Prize in Physics. But not until the year 2020, 55 years after he did it, when he was nearly 90 years old. The pattern holds even in the vindication. Even being right about the most important structural fact of black holes bought Penrose more than half a century of waiting for the recognition. Think about what Penrose actually proved, stated plainly, because the field spent decades softening it, and it deserves to be said without cushioning. General relativity does not merely permit the singularity, it demands it. The theory says that when a large enough star dies, the collapse does not stop at a neutron star, does not stop at any dense but finite object, does not stop anywhere. It runs all the way down to the point where the theory itself breaks. The most successful description of gravity ever written predicts, as a robust and generic outcome, the creation of a place where that same description fails completely. The theory guarantees its own blind spot. It manufactures, by the billions, objects at whose hearts it goes blind. And there is no version of realistic collapse where this does not happen. Once the trapped surface forms, the abyss is not a risk. It is a promise. It was around this time, in 1967, that the thing finally got its name, and the name came from a man who had started out as one of the skeptics. John Archibald Wheeler was a titan of American physics, a man who had worked on the atomic bomb and taught a generation of the field's best minds, and for years he had been deeply uncomfortable with the idea of complete gravitational collapse. But by the mid-60s, the mathematics and the new astronomy had worn down his resistance, and Wheeler did what the truly great scientists do. He changed his mind, and then he threw his considerable authority behind the thing he had once doubted. At a conference in late 1967, reaching for a phrase to replace the clumsy term gravitationally completely collapsed object, Wheeler used the words black hole, and the name stuck so completely that it is now almost impossible to believe the concept went without it for over 50 years. Schwarzschild had written down the solution in 1916. The object it described did not even have a name until 1967. For half a century, the most extreme prediction of general relativity was a thing physics could not bring itself to name, because to name it would have been to admit it was real. And by the time it had a name, the sky had already begun handing over the evidence that it was. In 1963, an astronomer named Martin Schmidt was studying a strange star-like object called 3C273, a point of light that turned out to be billions of light-years away and yet was outshining entire galaxies. These objects, quasars, were pouring out more energy than hundreds of billions of stars from a region no bigger than our solar system, and the only mechanism anyone could find that fit was matter spiraling into a supermassive black hole, releasing gravitational energy as it fell. In 1967, a graduate student named Jocelyn Bell working in Cambridge detected a precise repeating pulse from space, and the source turned out to be a neutron star, the collapsed core of a dead star packed to nuclear density, spinning many times a second. Neutron stars were the proof of concept the whole subject had been missing. They showed that stellar collapse into an object of unthinkable density was not a fantasy. It happens. Stars really do fall in on themselves and become something monstrous and small. And a neutron star is only one step from the edge. Pile on a little more mass, push past the point where even nuclear matter can hold, and there is nothing left in the known laws of physics to stop the fall. Then came the individual object that turned the argument. In the constellation Cygnus, a fierce source of X-rays called Cygnus X1 was found to be a system where a visible star was orbiting something unseen, something compact, something with a mass far too large to be a neutron star and far too small and dark to be an ordinary star. The X-rays were coming from gas being torn off the visible star and heated to millions of degrees as it spiraled into the invisible companion. By the early 1970s, Cygnus X1 was the first object that the community broadly accepted as a black hole. An actual location in the actual sky where Schwarzschild's abyss appeared to be sitting, feeding. Even then, the caution ran so deep that two of the era's leading physicists, Stephen Hawking and Kip Thorne, made a formal bet in 1974 over whether Cygnus X1 really contained a black hole, with Hawking taking the position that it did not, as a kind of insurance policy against his own hopes. He conceded the bet in 1990, admitting the evidence had become overwhelming. The man who understood black holes better than almost anyone alive had bet against their existence, and lost within his own lifetime. But even a lost bet in a sky full of circumstantial evidence is not the same as looking the thing in the face. And for most of the 20th century, that was the honest state of affairs. We had the mathematics. We had objects that behaved exactly as black holes should behave. What we did not have was direct proof, a signal that could have come from nothing else. The abyss caught in the act with no room left to doubt. That proof arrived twice within a few years of each other, a full century after Schwarzschild mailed his letter, and both times it landed with the force of something that should have been front-page news for a month, and instead flickered across the feed for a day. The first arrival was on the 14th of September, 2015. Two enormous detectors in the United States, together called the Laser Interferometer Gravitational Wave Observatory, or LIGO, each one an L-shaped tunnel with arms 4 kilometers long, measured a ripple passing through space-time itself. The ripple was the death cry of two black holes, one about 36 times the mass of the Sun, and the other about 29, that had been orbiting each other and had finally spiraled together and merged into a single larger black hole. About 1.3 billion light-years away, in the final fraction of a second before they became one, they radiated more power in gravitational waves than all the stars in the observable universe combined, and that power, stretched thin across 1 billion light years and 1 billion years of travel, arrived at Earth as a wobble in the length of those 4-kilometre arms smaller than 1,000th the width of a proton, and the machines caught it. The waveform matched the predictions of general relativity for 2 horizons merging with a precision that left no serious room for any other explanation. We had heard 2 black holes collide, the abyss had a sound, and we had recorded it. The second arrival was on the 10th of April, 2019. A collaboration called the Event Horizon Telescope, which had linked radio observatories across the entire planet into a single Earth-sized instrument, released an image. It was blurry and orange, and it looked, to an untrained eye, like almost nothing, a fuzzy ring of light with a dark hole at its centre. That dark hole was the shadow of the event horizon of a supermassive black hole at the heart of a galaxy called M87, an object about 6.5 billion times the mass of the Sun, some 55 million light-years away. The bright ring was superheated matter glowing as it circled the drain. The darkness in the middle was the region from which no light can escape. Projected onto the sky, the silhouette of Schwarzschild's radius drawn in shadow against a background of fire. For the first time in human history, we were looking at a black hole. 3 years later, in 2022, the same collaboration released an image of the black hole at the centre of our own galaxy, Sagittarius A star, 4 million times the mass of the Sun. Sitting 26,000 light-years away in the direction of the constellation Sagittarius, the dark heart around which our entire galaxy and our Sun and this planet and you have been slowly turning for the whole of your life. And that dark heart is not an inference from a blurry photograph alone. For nearly 30 years, 2 rival teams of astronomers, one led by Reinhard Genzel in Germany and one led by Andrea Ghez in California, have been doing something that sounds impossible. They have been watching individual stars orbit the invisible object at the centre of our galaxy, night after night, year after year, plotting their paths the way you would plot a planet going around the Sun. There is a star, catalogued as S2, that swings around Sagittarius A star on an orbit that takes about 16 years to complete, and at its closest approach it is moving at nearly 8,000 kilometres every second, which is close to 3% of the speed of light, whipped around by the gravity of something it is orbiting at terrifying speed. And from the shape and the speed of that orbit, and the orbits of dozens of other stars near it, you can calculate exactly how much mass they are all circling, and where it has to be. The answer is about 4 million times the mass of the Sun, packed into a region smaller than the orbit of the planets around our own star, emitting almost no light of its own. There is nothing in physics that can be that massive, that compact and that dark, except the thing Schwarzschild found. Genzel and Ghez were awarded the Nobel Prize in Physics in 2020, sharing it with Roger Penrose, for tracking those stars and proving what they orbit. We are not inferring the black hole at the centre of the galaxy from theory. We have watched stars fall around it for 3 decades and clocked their speed, and it is worse than one dark object sitting quietly at the middle of the Milky Way, because these supermassive black holes turn out to be at the centre of nearly every large galaxy, and their masses are locked in a tight relationship with the galaxies around them. The bigger the central bulge of a galaxy, the bigger its central black hole, in a correlation so clean that it points to something disturbing. The galaxy and the abyss at its heart appear to have grown up together, shaped each other, co-evolved. Which means the black hole is not some accident that happened to fall into the middle of the galaxy after the fact. The galaxy seems to have been built around it. The quasars I mentioned, those distant beacons outshining hundreds of billions of stars, are these same supermassive black holes in their feeding youth, blazing as they devoured matter in the early universe. The The abyss is not a rare visitor to the cosmos. It sits at the structural center of the largest objects there are, and everything else. All the stars, all the light, all the worlds is arranged around it. The debate is over. This is not fringe, and it is not theoretical, and it has not been either of those things for a long time. The object Einstein published a paper to disprove has been heard colliding and photographed twice. Schwarzschild was right. The abyss is real, it is common. There is one at the center of nearly every large galaxy, including our own, and the outer threshold he found in 1916, the radius that bears his name, is now something we can point a planet-sized camera at and see as a circle of pure darkness. That much is settled. But settling the existence of the thing did nothing to settle the question we started with, the one underneath everything. And this is where the story stops being a triumph and turns back toward the dark. Because now that we know the abyss is real, the singularity at its center is real too, which means the place where the laws of physics fail is a real place, sitting inside real objects scattered by the billions across the real sky. We have not explained it. We have only confirmed that it is there. And what actually happens at that point, what becomes of everything that falls in, is a question that has driven the deepest minds in physics into a corner they have not escaped from in 50 years. And the more carefully you follow it, the more it starts to look as though the universe is not merely hiding the answer, it is engineered to hide it. Start with what the horizon does to time, because it is the first sign that this object does not merely trap things, but keeps them in a way that is genuinely eerie. I told you earlier that if you fell into a black hole, you would cross the horizon without feeling anything. And that is true from your point of view. But from the point of view of someone watching you fall, something very different happens. As you approach the horizon, they see your clock running slower and slower. Your falling body appears to descend more and more sluggishly, never quite reaching the boundary. The light coming off you stretches to redder and redder wavelengths and dims, and from the outside, you are never actually seen to cross. You slow, you redden, you fade, and you hang there, frozen, at the edge, forever. This is why the early Russian physicists who studied these objects called them frozen stars. From the outside, a black hole is a monument to everything that has ever fallen toward it. Every particle smeared across the approach to the horizon, slowed to near stillness, held in the last instant of its fall for the entire future history of the universe. The abyss does not just swallow, it preserves the moment of swallowing, stretched to eternity, on its surface. Everything that ever fell in is, in a sense the mathematics takes completely seriously, still falling. And what sits at the center, the singularity itself, the point where the theory dies, is never visible from outside at all. It is always wrapped in a horizon, always hidden. You cannot see a singularity from the safe side, because the horizon forms around it and seals it off before the breakdown of physics is ever exposed to the outside universe. And this turns out to be so consistent, so reliable, that Penrose elevated it into a formal conjecture in 1969, and gave it a name that I think is one of the most revealing names in all of physics. He called it cosmic censorship. The conjecture states that nature never permits a naked singularity, a place where physics fails that is visible to the rest of the universe, unclothed by a horizon. Every singularity, the conjecture says, comes wrapped, hidden, censored. Its lawless heart always tucked behind a surface that no signal can cross. Sit with the language physicists reached for, because they did not choose it lightly. They did not call it the horizon closure property or the singularity containment theorem. They called it censorship, as though something were doing the censoring, as though the breakdown of physical law at the center We're a fact the universe permits to exist, but does not permit to be seen. A secret that reality keeps sealed behind a one-way surface, always, everywhere, without exception. And here is the part that should get under your skin. Cosmic censorship has never been proven. It is a conjecture, one of the great open problems, and no one has been able to show that nature truly forbids a naked singularity in every case. All we have is the observation that so far, in every situation we can model, the breakdown stays hidden. The universe keeps its lawless places covered. We do not know why, we only know that it does. But the horizon hiding the singularity is not even the deepest strangeness here, because in 1974 a young Stephen Hawking discovered something that turned the black hole from a place where things are kept forever into a place where things might be erased forever, and the difference between those two, keeping and erasing, is where physics currently stands broken against a wall it has not climbed in 50 years. Hawking combined general relativity with quantum mechanics near the horizon, something no one had done carefully before, and he found that black holes are not perfectly black. Because of quantum effects right at the edge of the horizon, a black hole slowly radiates a faint glow of particles, now called Hawking radiation, and in doing so it very gradually loses mass. Over unimaginable spans of time, far longer than the current age of the universe, a black hole will evaporate. It will shrink and radiate and shrink until it is gone. And this is where the wall appears, because the radiation that comes out is thermal. Random, it carries no detailed information about whatever fell in. Picture everything that ever fell into a particular black hole, every star, every planet, every book and body and encoded memory, all of it crossing the horizon and falling toward the center, and then imagine the black hole slowly evaporating into featureless random radiation and vanishing. Where did the information go? Everything that fell in described a specific arrangement of matter, and quantum mechanics has an ironclad law, one of its most fundamental, that says information can never be truly destroyed. The precise quantum state of the past must always be recoverable in principle from the present. And yet the black hole appears to take all of that information, seal it behind a horizon, and then erase it from existence as it evaporates into random heat. General relativity says the information falls to the center and is lost. Quantum mechanics says information cannot be lost. Both theories are the most tested and most successful in the history of science, and at the black hole they contradict each other flatly, and no one has resolved it in a way the whole field accepts. This is the black hole information paradox, and it has consumed the careers of many of the most capable physicists alive for half a century. It is worth slowing down on how a black hole can radiate anything at all, because the mechanism is nearly as strange as the paradox it produces. Empty space, according to quantum field theory, is not empty. It seethes. Pairs of particles, a particle and its antiparticle, are constantly flickering into existence and annihilating back into nothing, borrowing a little energy from the vacuum for the briefest permitted instant, and then paying it back before the universe can catch the debt. This is not speculation. The measurable effects of these fleeting pairs have been confirmed in the laboratory to extraordinary precision. Now picture this happening right at the edge of a horizon. A pair flickers into being straddling the boundary. One of the two falls in. The other escapes, and the one that escaped can no longer find its partner to annihilate with, because the partner is gone forever beyond the horizon. So it is promoted into a real lasting particle, flying away from the black hole and carrying energy with it. That energy has to be paid for, and it is paid for by the black hole itself, which surrenders a sliver of its own mass to cover the particle that got away. Multiply that theft over the entire surface of the horizon, across enormous spans of time. and the black hole slowly bleeds itself away into a thin haze of escaping particles. The abyss glows, faintly, by robbing pairs from the vacuum at its own edge and letting one twin flee while it swallows the other. And the feature that makes this stranger still is that the temperature of the glow runs backward from every intuition you have about heat. It is inversely proportional to the mass. The largest black holes are colder than the coldest thing you could construct, radiating so faintly that they take in more warmth from the faint background glow of the sky than they give off, which means that in the present universe they are still growing, not shrinking. But a black hole that does lose mass gets hotter, and hotter means it radiates faster. And radiating faster means it loses mass faster still, a runaway that ends, in the final instant, with the black hole flaring up and detonating in a last burst of high-energy radiation. The timescales defeat comprehension. A black hole with the mass of the Sun would take on the order of 10 to the 67th power years to evaporate, a span so much larger than the current age of the universe that the comparison carries no meaning. The supermassive ones would need 10 to the 100th power years or more. These are not really durations. They are closer to a definition of forever. But forever is not the same as never, and that gap is the entire problem. It means the black hole is not eternal. It is temporary. Given enough time, it will be gone, and when it is gone, the question of where everything it swallowed went can no longer be pushed off into the indefinite future. A permanent black hole could keep its secret behind the horizon forever, and no one could ever prove the record had truly been destroyed. An evaporating one cannot. It hands the universe a deadline. Eventually the hole finishes bleeding out, the horizon vanishes, the shield is gone, and whatever was sealed inside must have gone somewhere. And general relativity and quantum mechanics answer that question in flat, irreconcilable contradiction. Follow that all the way out, past the death of the stars, and sit with where it leads. Everything that has ever fallen into a black hole is right now sealed behind a horizon that is, with unimaginable slowness, evaporating, on a long enough timescale, far longer than the age of any star or galaxy. The black holes themselves become the last large structures remaining in a cold and emptying cosmos, and then even they finish bleeding away into a faint fog of radiation and wink out, one after another, until there is nothing left but that thinning fog cooling toward perfect stillness. And in that final radiation, if general relativity is right about what happens at the center, the specific identity of everything that ever fell in has been dissolved into featureless heat, the past rendered permanently unrecoverable, the universe having quietly forgotten itself. Unless the record somehow survived, written on the vanishing surface, carried out in correlations too subtle for anyone to have yet decoded, in which case the memory is preserved, but the smooth, simple horizon that Schwarzschild's radius describes is not the whole truth after all. Half a century of the finest minds in the field, and those remain the only two doors out of the room. And each one shatters something we were certain of. I want to dwell on what this contradiction actually implies, because it is easy to let the phrase information paradox slide past as an abstraction, and it is not abstract at all. Information, in physics, is not a metaphor. It is the specific arrangement of everything, the exact configuration that distinguishes you from a cloud of the same atoms scrambled. The claim that information cannot be destroyed is at bottom the claim that the past leaves a permanent imprint on the present, that reality never truly forgets, that in principle every detail of everything that has ever happened is still encoded somewhere in the quantum state of the universe right now. That is one of the deepest commitments in all of physics, and the black hole appears to break it. The abyss appears to be the one place in the universe where the past can be genuinely erased, where the record can be destroyed, where reality can forget. Either that, or general relativity is wrong about what happens at the horizon, and the information secretly escapes in a way we do not yet understand, which would mean the smooth, featureless horizon that Schwarzschild's radius describes is not the full story either. There is no comfortable option. One of the two pillars holding up modern physics has to give, and at the centre of the thing forcing the choice is the singularity Schwarzschild found on a battlefield in 1916. There is a clue, and the clue is itself unsettling. The leading attempts to save the information point to the horizon, the surface, as the place where the record is somehow stored. There is a deep result from Hawking himself and from Jacob Bekenstein before him that the amount of information a black hole can contain is proportional not to its volume, as you would expect for anything that stores things inside itself, but to the area of its horizon, the surface. As though everything that fell in were not really buried at the centre but written on the boundary, encoded on the two-dimensional surface of the Schwarzschild radius like text on a page. This is the origin of what is now called the holographic principle, the growing suspicion among theoretical physicists that the three-dimensional interior of a region might be fully described by information living on its two-dimensional boundary, that depth itself might be a kind of projection. And if that is right, then the horizon is not just a trapdoor, it is a ledger. It remembers. Everything that ever fell in is written on the surface, and the interior, the falling, the descent toward the centre, might be in some sense a shadow cast by information encoded on the skin of the abyss. The universe, it seems, keeps its books at the edge of the hole. I am going to be honest with you, because this document was built by someone who has spent an unreasonable number of hours inside this material, and I would be lying if I pretended otherwise. I do not know how to think about this. Nobody does. The situation, stated as plainly as I can manage, is that reality contains objects at whose centres our best physics fails completely. That reality always hides those centres behind a surface no signal can cross. That reality may or may not permit the past to be erased at those centres in violation of its own deepest law, and that the only hints we have point toward the surface of the whole recording, in some form we do not understand, everything the whole has ever taken, and all of it traces back to a single exact solution, mailed from a trench by a man who found the place where the description of reality dissolves into infinity at the same time his own body was dissolving under a disease with no name he could have understood and no cure anyone could offer. Because this is what I have been circling since the beginning, the thing I planted early and have not yet let land. The singularity is where general relativity predicts its own death. It is the point built into the foundation of our theory of space and time, where space and time stop meaning anything. It was not added later. It was not a correction or an amendment or a strange special case discovered decades in. It was there in the very first exact solution to the theory, the first time anyone solved Einstein's equations cleanly, on paper, in 1916. The whole was in the answer from the beginning. The moment general relativity received its first exact solution, that solution contained, at its heart, the place where general relativity destroys itself. And the man who reached in and pulled out that first exact answer, who was the first human being to hold the complete description of the field around a mass, and therefore the first to see the infinity waiting at the bottom of it, had, at that moment, only a few months left to live. Therefore we have to go back to him. We have to go back to Karl Schwarzschild, to the trench, to the disease, to the exact nature of what was happening to his body while he did the work, because the parallel I have been resisting stating outright is the whole reason this story does not leave you when the video ends, and it is time to stop resisting it. To understand who was holding the pencil, you have to go back to a boy in Frankfurt with a telescope. Karl Schwarzschild was born on the 9th of October, 1873, into a Jewish family in Frankfurt am Main, the eldest of a large family. His father, a businessman, with no particular scientific bent. And the boy was, by any measure anyone has ever applied, a prodigy of a kind that comes along rarely. As a child, he saved his money to buy lenses and built his own telescopes. And by the age of 16, an age at which most gifted students are still learning the shape of the field, Schwarzschild had written 2 original scientific papers on celestial mechanics, on the theory of the orbits of double stars, and had them published in the Astronomische Nachrichten, one of the leading astronomical journals of the day. A 16-year-old publishing real original work on how pairs of stars move around each other under gravity. He was mapping the geometry of orbits before he could vote, and there is something almost unbearable, given where the story ends, about the fact that his life in science began and ended with the same subject. Gravity and the shapes it forces matter to trace. He studied at Strasbourg and then at Munich, and he took his doctorate in 1896, at the age of 22, with a dissertation on the theories of Henri Poincaré concerning the equilibrium shapes of rotating fluid masses. Read that again with the rest of the story in mind. His doctoral work was on how a spinning body of fluid arranges itself under its own gravity, which is, in a very real sense, the ancestor of the entire problem of stellar structure, the problem of how a star holds itself up, the problem whose failure at the high mass end is exactly what produces the collapse into a black hole. The threads of his life do not merely connect to the abyss. They point at it from the very beginning, decades before Einstein had written down a single field equation. Schwarzschild spent his whole career circling the physics of self-gravitating masses, and then in the last months of his life the deepest secret of self-gravitating masses fell into his hands and killed him, and he was the perfect person in all the world to have found it, and the worst possible person to lose. His rise was rapid and total. He worked in Vienna, and then in 1901, at the age of 28, he became a full professor and the director of the observatory at Göttingen, which at that moment was arguably the greatest concentration of mathematical genius on the planet. The Göttingen of that era was the Göttingen of David Hilbert and Felix Klein and Hermann Minkowski, the beating heart of world mathematics. And Schwarzschild belonged there, holding his own among titans, respected across the entire spectrum of the mathematical and physical sciences. And his range was staggering, genuinely universal in a way that had already become rare even then. He did foundational work on the transfer of radiation through the atmospheres of stars, work that still underlies how we read the light of the sun. He studied the behaviour of photographic emulsions so precisely that a correction factor in photographic exposure still carries his name. He worked in optics, designing telescope systems of a type still referenced today. He worked in electrodynamics, in geometrical optics, in spectroscopy, in the mechanics of comet tails. There was hardly a corner of physics or astronomy he touched without leaving something behind. In 1909, he was appointed director of the Astrophysical Observatory in Potsdam, the most prestigious position in all of German astronomy. He was, by 1914, one of the most accomplished and respected scientists in Europe, 40 years old, secure, celebrated, with a wife and children and every reason in the world to stay exactly where he was. And when the war came, he volunteered. He did not have to. Nobody of his age and stature and value was expected to put on a uniform and go to the front. He was 40 years old and one of the intellectual treasures of the nation, the kind of man a country protects, not the kind it sends toward artillery. But he went, out of a sense of duty that the modern reader may find difficult to fully inhabit, and the army, in its wisdom, took one of the finest mathematical minds of the century and set it to computing the trajectories of shells. He served first in Belgium, at a weather station, then in France, and finally on the Eastern Front in Russia, an artillery lieutenant calculating firing tables. The arcs and angles that would drop high explosive onto men he would never see. There is a bitterness in that image that I do not think can be fully drained. The man who was about to solve Einstein's equations for the geometry of space-time around a mass was spending his days solving the far simpler, older, deadlier Newtonian equations for the geometry of a shell's flight toward a target. And it was there, in that setting, sick and surrounded by the machinery of killing, that he did the last and greatest work of his life, and the detail that stops me every time I return to it is that the black hole solution was not even the only frontier of physics he pushed forward from that trench. 1916 was a hinge year for two separate revolutions in physics. General relativity on one side and the new quantum theory of the atom on the other, and Karl Schwarzschild, dying on the Russian front, contributed to both of them in the same handful of months. Alongside the two relativity papers, he worked out a treatment of how an electric field splits the spectral lines of atoms, the phenomenon called the Stark effect, using the brand new quantum rules of Bohr and Sommerfeld, introducing techniques that would matter for the development of quantum theory. Both of the great pillars of 20th century physics, relativity and quantum mechanics, the very two theories that we now know contradict each other precisely at the black hole, were advanced by the same dying man at the same front, in the same season of his life. He had a hand in building both of the pillars that the abyss he discovered would later be found to crack apart. If you tried to write that as fiction, an editor would tell you it was too much, that no one would believe a single obscure artillery officer touched both frontiers at once in his final months. But the papers exist. The dates are real. He did all of it while the disease was already inside him, already beginning the work that would finish him before the year was out. Because he was, by this point, already dying, and the way he was dying is the part of this story I find genuinely hard to talk about without feeling that the universe was making a point too cruel to be accidental. Therefore, we have to talk about the disease, and about what it actually does to a body, because once you understand what was happening to Karl Schwarzschild's flesh while he mapped the place where the description of reality dissolves, the parallel stops being a poetic flourish and starts to feel like something closer to a signature. The disease was called pemphigus, and in 1916 it was a death sentence with no appeal. It is a rare autoimmune disorder, and to understand what it does you have to understand that your skin is not a single sheet, but a structure of individual cells held tightly together by microscopic molecular rivets, specialized proteins whose entire job is to bind one skin cell to the next and maintain the barrier that separates the inside of you from the world. In pemphigus, the immune system, the very system whose purpose is to defend the body, turns and attacks those rivets. It produces antibodies against the proteins that hold the skin together, and once those bindings are attacked, the skin cells come apart from one another. The barrier fails. Blisters form as the layers separate, then rupture, leaving raw open wounds. And the process spreads across the skin and through the moist linings of the mouth and throat, and the body loses the ability to maintain the boundary of itself. Before the arrival of corticosteroids and immune-suppressing drugs decades later, pemphigus was very nearly always fatal. In 1916 there was nothing to be done. The medicine of the time could only watch. Now hold that next to what he had just discovered, and tell me it does not do something to you. Karl Schwarzschild found the place where the boundary of physical description fails, the horizon beyond which the inside is severed from the outside, and the center where the very integrity of space and time comes apart. And he found it while his own body was suffering a disease in which the boundary between his inside and the outside was failing, in which the structures that held him together were coming apart, in which the system meant to preserve him had turned against the rivets that maintained his own edge. He mapped the collapse of the description of reality with a body that was itself undergoing a collapse of its own integrity. The man who first described the surface beyond which nothing can be held together was dying because the surface of his own body could no longer hold itself together. I have gone looking, more than once, for a way to talk myself out of finding this meaningful, and I have not managed it. The dates are the dates. The disease is the disease. The solution is the solution. They happened in the same body, in the same months, in the same trench. I want to be careful and honest here, because this channel does not exist to feed you a myth, and the honest version is actually heavier than the mythic one. It is often implied that the front gave him the disease, that the war and the cold and the horror somehow triggered the illness, that the trench reached into him and did this. There is no good evidence for that. Pemphigus is an autoimmune condition, and its deep causes are still not fully understood even now, and the idea that the artillery front caused it specifically is not something the record supports. It may well have been coincidence, a catastrophe of his own immune system that would have come for him regardless of where he was standing. And in a way that is worse, because it strips away the consoling narrative that the war killed him. The war did not kill him. His own body killed him on its own schedule, indifferent to everything, at the precise moment he was doing the greatest work of his life. There was no villain. There was no cause you could be angry at. There was just a man's own biology turning against the boundaries that held him, at random, at the exact wrong time, while his mind was more lucid and more productive than it had ever been. That is not a story with a moral. That is just what happened. The timeline of his decline is short and merciless. The first exact solution reached Einstein and the Prussian Academy in January of 1916. The second paper, on the interior geometry of a mass, reached Berlin in late February, and by then the disease was already advancing across his skin, on the Russian front in winter. He grew too ill to remain at the front, and he was invalided home to Germany in the early months of the year. There was no treatment to give him. He went home to Potsdam to the observatory he had directed, and the illness ran its course through him, and on the 11th of May 1916, Karl Schwarzschild died. He was 42 years old. 4 months earlier he had handed the world the first exact solution to general relativity, and folded inside it the first description of a black hole. And in those 4 months, not one other person on Earth had understood what he had actually found. He died with the abyss known to no one but himself, and even he did not fully grasp what he was looking at, because the framework needed to understand it, the trapped surfaces and the coordinate analysis and the collapse dynamics, would not exist for another 40 to 50 years. He found the bottom of the theory and then he was gone, and the answer he mailed out sat in a journal, correct and complete and unread for what it was, while the men who came after argued for half a century about whether it meant anything. Einstein gave the memorial address. On the 29th of June 1916, before the Prussian Academy of Sciences in Berlin, the same body to which Einstein had read Schwarzschild's papers a few months earlier while their author lay dying, Einstein delivered the eulogy for the man who had solved his equations. He spoke of the extraordinary range of Schwarzschild's mind, of the rare and striking combination in one person of deep theoretical power and real practical observational skill. The mathematician and the astronomer fused in a single man. He praised the versatility, the reach, the sheer breadth of what Schwarzschild had been able to do. It was a genuine tribute from one great mind to another, and it was sincere. And here is the quiet irony sitting underneath it, the one that only becomes visible with a century of hindsight. Einstein stood there and honoured the man who had found the exact solution to his theory, and Einstein had no idea, could not have had any idea, that the solution he was praising contained a monster he would spend the next 23 years of his own life trying to prove could not exist. He eulogized Schwarzschild in 1916, And in 1939 he published his paper arguing that the object at the heart of Schwarzschild's solution was a physical impossibility. He honoured the man, and then he spent decades denying the man's deepest discovery, and he never knew that was what he was doing, because he never lived to see the 1960s prove Schwarzschild right and himself wrong. Einstein died in 1955. The vindication of the black hole, the moment physics finally accepted the abyss as real, arrived a decade after Einstein was already gone. Both of them, the man who wrote the equations and the man who solved them, died before the world understood what the two of them had built together, and neither of them got to see it. But the story does not quite end at the grave in Potsdam, because Karl Schwarzschild left behind a son, and what that son grew up to do closes a circle so precise that it feels less like biography and more like the universe rhyming with itself on purpose. Therefore, we have to follow the name forward one more generation, and then we have to go all the way down to the bottom of the thing. To the implication I have been walking you toward since the first minute, the one that does not let go. When Karl Schwarzschild died in May of 1916, he left a son who had just turned 4 years old. The boy's name was Martin Schwarzschild, born in Potsdam in 1912, and he would grow up to become one of the most important astrophysicists of the 20th century. And the subject he devoted his life to is the reason I cannot tell this story without a chill. Martin Schwarzschild became a founding figure in the modern theory of how stars are born, how they live, and above all, how they die. He fled Germany in the 1930s as the Nazis rose, and the country made clear it had no place for a family of Jewish descent. And he made his way eventually to the United States and to Princeton, and during the Second World War he served in the army of his adopted country, an intelligence officer in Europe, which means that both Schwarzschild men, father and son, put on a uniform and went to a world war for the nation they lived in. But it is his science that closes the circle. Martin Schwarzschild worked out, in detail that had never existed before, the life cycles of the stars. Using some of the first electronic computers, he modelled what happens inside a star as it exhausts its nuclear fuel, how it swells and changes and moves toward its end. His book, Structure and Evolution of the Stars, published in 1958, became a foundation of the entire field. He spent his career mapping the road that leads a star to its death. Think about what that means as a pair. The father found the mathematics of the endpoint, the exact geometry of what a dead star becomes when it falls all the way down, the black hole at the bottom of the collapse. The son spent his life mapping the road that leads to that endpoint, the slow biography of a star from birth to exhaustion. Between the two of them, across 2 generations of the same family, the Schwarzschilds described the entire arc of stellar death, the son tracing how a star arrives at the edge, the father describing the abyss waiting at the bottom of the fall. The father died before anyone understood the abyss. The son lived until 1997, long enough to see the black hole fully vindicated, long enough to see the objects his father had first described accepted as real and common and central to the structure of the universe. The son got to watch the world finally believe the father, and I do not know whether that is a comfort or the opposite, that the vindication his father never lived to see came home to the man's own child, who had been 4 years old when the disease took him. And then there is the name itself, which I hesitated to even mention because it sounds like the kind of thing a lazy writer invents, except that it is simply true, and anyone who speaks German can confirm it in a second. Schwarzschild, in German, Schwarz means black, and Schild means shield or sign. The man's surname, the name he was born with, the name now permanently attached to the radius that surrounds every black hole in the universe, literally means black shield. Black shield. The event horizon is precisely that. It is the black shield around the singularity. the surface that cosmic censorship wraps around the place where physics fails, the dark barrier that hides the breakdown of reality from the rest of the universe and shields us from ever seeing it directly. A man named Black Shield discovered the Black Shield. I am not going to pretend that this means anything. Coincidences of names are just coincidences, and the universe is not writing puns into the birth certificates of German astronomers, but it is there, in the record, an accident so precise that it has been remarked on by physicists and historians for decades, and once you know it, the name on the radius stops sounding like a label and starts sounding like a description that was somehow assigned before the thing it describes was even known to exist. I have given you the whole story now. The prodigy who published on the geometry of orbits at 16. The universal scientist who touched every corner of physics. The 40-year-old who volunteered for a war he did not have to fight and was set to computing the flight of shells. The man who, in a trench on the Russian front, in the last winter of his life, reached into Einstein's brand new equations and pulled out the first exact solution anyone had ever found, and discovered at the bottom of it a place where space and time trade roles, and a centre where the description of reality dissolves into infinity. The disease that was at that same moment dissolving the boundaries of his own body, unravelling the structures that held him together, on no schedule but its own. The death at 40, 4 months after the discovery, with not a single other human being alive who understood what he had found. The 50 years of refusal that followed, Einstein himself leading the denial, publishing a paper to prove the abyss impossible, dying before he could be proven wrong. And the slow, reluctant, overwhelming vindication, the trapped surfaces and the collision heard by LIGO, and the shadow photographed against the fire, that finally forced physics to admit the thing had been real the entire time, sitting in the sky in enormous numbers, waiting for our permission that it never actually needed. But a story is only the surface, and I told you at the start that underneath it there was a single question we were not going to answer, and it is time to go all the way down to it, past the biography, past the history, past the vindication, to the thing that is actually at the bottom of all of this, and that does not resolve and does not comfort, and does not let you set it down when the screen goes dark. Because the discovery Schwarzschild made is not, in the end, a discovery about a strange object out there in space. It is a discovery about the theory itself, about the description of reality that we hold to be our most successful and most trustworthy account of what space and time actually are, and what that discovery says when you follow it all the way down, is something I genuinely do not know how to live with, and I am not sure anyone does. General relativity is not a theory that occasionally stumbles. It is the most precisely tested description of reality that human beings have ever produced. It predicted the bending of starlight around the sun, and we saw it. It predicted the slow shift in the orbit of Mercury, and there it was. It predicted that clocks run slower deeper in gravity, and every satellite navigation system on Earth has to correct for exactly that effect, or it would give you the wrong street within hours. It predicted ripples in space-time from colliding masses, and 100 years later 2 machines in America caught the waveform of 2 black holes merging 1 billion light years away, and it matched the equations to a precision that beggars belief. This theory does not miss. It is the crown jewel of physics, the closest thing we have to a direct reading of what space and time actually are. And this theory, our most trustworthy account of the fabric of reality, predicts with total confidence the existence of places where it stops working entirely. Not at the ragged edge of its validity, not in some regime it was never built to handle. At the centre of an object it insists must form, that it guarantees will form through Penrose's proof, whenever enough matter falls together. Our best description of reality builds into its own foundation the coordinates of the place where it goes blind. It draws the map, and then it marks, with an infinity, the spot where the map dissolves, and it tells you that spot is real and common and waiting at the heart of every collapsed star in the sky. And the universe hides every single one of them. This is the part that stopped being physics for me somewhere along the way and started being something harder to name. Every place where the laws break down comes pre-wrapped in a horizon, a surface no light can cross, a black shield sealing the breakdown away from view. In every case we have ever been able to examine, the wound is covered. The universe does not permit a naked look at the place where its own laws fail. We have a name for this, cosmic censorship, and we cannot prove it holds in general, and yet it holds everywhere we look. Reality manufactures, by the billions, points at which its own description collapses, and then reality shields every one of those points behind a surface that guarantees no one on the outside will ever see the collapse directly. If you did not know better, you would say the universe is keeping something from us, that it builds these breakdown points as a matter of routine and then, without a single exception we have found, refuses to let us look at them. And what it does with everything that falls in may be worse than hiding. Remember the information paradox, the collision between general relativity and quantum mechanics at the horizon. Quantum mechanics holds, as one of its most sacred principles, that information is never destroyed. That the past is always in principle recoverable from the present, that reality never truly forgets. And the black hole appears to be the one place in existence where that principle breaks, where the record of what fell in can be erased as the whole evaporates into featureless radiation, which means the abyss is not only the place where the laws of space and time fail, it may also be the place where the deepest law of all, the law that the universe keeps a perfect memory of itself, comes apart. The singularity is not a thing sitting inside reality like a rock at the bottom of a well. It is the edge of reality's ability to describe itself, folded into the center of an object that the universe assembles every time a large enough star burns out and falls down. And there is one of them, 4 million times the mass of the sun, at the center of the galaxy you are turning inside of right now. The dark anchor around which the sun and this planet and every person you have ever loved have been slowly orbiting for the entire length of your life, and it has been there the whole time, sealed behind its shield, keeping whatever it has taken. That is the thing Karl Schwarzschild found. Not a strange star, not an exotic curiosity out at the fringe of what physics allows. He found the place where our description of reality ends, and he found that reality builds that place on purpose, over and over, and hides it every time. He found it first, before anyone, in the first exact solution the theory ever yielded, which means the hole was in the answer from the very beginning. The moment general relativity was solved cleanly for the first time, the solution contained, at its heart, the coordinates of the theory's own death. It was never added later. It was there in the first clean answer, waiting, the way it had presumably been waiting in the structure of reality since long before there were minds to be disturbed by it. He wrote to Einstein that the war had been kind enough to let him take a walk in the land of Einstein's ideas. He did not know that the walk had taken him to the edge of the map. He did not know the edge was real, or that reality manufactures the edge by the billions, or that it would take the rest of physics 50 years and the death of Einstein himself before anyone would admit he had been standing at the true bottom of the theory. He mailed out the coordinates of the place where reality stops being describable, and then the boundaries of his own body began to fail, the structures that held him together coming apart on a schedule that answered to nothing, and he died at 42 with the abyss known to no one but him, uncomprehended even by him, sealed in a journal like everything the universe seals, waiting for a world that was not ready. The abyss is still there. It is at the center of the galaxy turning over your head tonight, and at the center of nearly every galaxy in the sky, and at the end of nearly every large star that has ever run out of fuel and fallen down into the dark. The theory that found it still dies at its heart, exactly where Schwarzschild's ink ran out. Cosmic censorship still holds, in every case we can check, and we still do not know why. The information paradox is still open, half a century on, the two greatest theories in physics still contradicting each other flatly at the one place we cannot see. And whatever is written on the surface of that darkness, the record of everything it has ever swallowed, it is not going to show you, and it is not going to show anyone, because the single thing the universe has never once been caught permitting is a clear look at the place where its own laws end. Karl Schwarzschild found that place first. It was in the first exact answer the theory ever gave. His own edges failed as he wrote it down. He died before a single other person understood, and the world spent the next 50 years insisting he was wrong. He was not wrong. He was early. He walked into the land of ideas, and he found the hole at the bottom of it. And the hole is still there, and it is still sealed, and it is still keeping every secret it has ever taken, including his.